How we get started entering and defining variables in SPSS. For more detail about questions from a questionnaire, please see those specific videos. This is just going to give a general sort of introduction and overview to entering data and defining variables. Now this is a new data file in SPSS. You'll notice at the bottom you have two tabs. One is data view. This is for your data, and one is variable view, and this is for your variable names. When you enter variable names in this first row, those names are going to appear across the top as the column headings, replacing the var that's there right now. So let's have a go at that. My first column, if I've done a questionnaire, is always participant ID. So I'm just going to name this variable ID. We'll come to these other columns shortly. Let's have a look at our data view. You can see that my column heading now says ID because that's my variable name. So now in this first column here, I would enter data for my ID numbers. So let's just enter 5 participants. So 1, 2, 3, 4, 5. Okay, so now I've got a bit of data in. The data view is only for data. Never put variable names across the first row because you do not analyze variable names, you only analyze the data. Also, when you go to enter data, it should be numeric data, especially if you're going to analyze it. It's just good practice. I know that in SPSS you can kind of get away with not coding nominal variables, but it's good practice to code them anyway, because SPSS is a quantitative software. It's not meant for qualitative data. So let's go to variable view. We're going to enter some data. I'm going to enter 3 variables. I've got my participant ID. I'm going to enter a categorical variable, gender, and I'm going to enter a scale variable, which is travel time, and that's how long it takes someone to commute from their home into university. So I'm going to put my variable names in first. My second variable is gender, and my third variable is travel time. Now there's a couple rules when writing variable names. 1, they must begin with a letter. 2, they cannot contain a space. And 3, they cannot contain any special characters except for an underscore. So for travel time, I could put an underscore in between and that would be acceptable, but I cannot put a space. The second column is defining the type of data, numeric, string, date, etc. Most of your data will most likely be numeric. Occasionally you may have dates. Width, don't need to worry about that. It has to do with character width. Number of decimal places. This is how many decimal places you see in the data view. So all of my data does not have any decimals, so I'm going to reduce this to 0. Now you remember before my IDs had 1.00, 2.00, had 2 decimal places. Now those decimal places are gone. It's much easier to read if you don't need those decimal places. Now the label's really important. This is what's going to appear on all of your output for tables, charts, and graphs. So be a bit more descriptive. Gender, that doesn't need to change. Time it takes to travel. It's a good idea to specify units in your label as well, so my units are minutes. The next column is for value labels. You only need value labels for categorical data, so that means you tell SPSS what the codes mean. I'm going to code gender. I'm going to let 0 be male and click add, and 1 is going to represent female. These are the codes I've given. You can use 1 and 2 if you want. It doesn't really matter. I just prefer 0s and 1s. So go ahead and click OK. My travel time is scale, meaning it's not grouped in any way, so I don't need to put any value labels and I don't need anything for participant ID. If you decide to have a code for missing data, you can define it here. So say I coded my missing data as 999. I would put that code in here, and that means if SPSS came across a 999, it would consider it missing. You would need to do that for every variable where you have missing values. The last column we're going to have a look at is the level of measurement. If you're not sure about the level of measurement, please do have a look at the video I made about level of measurements in SPSS. our ID, we're never going to use the participant ID in any kind of analysis, so it really doesn't matter what you put. I'm just going to leave it as scale because it will never be used anyway. Now gender, that is categorical, male, female. The words give it away. Even though we have numerical codes of 0 and 1, it's not numeric, it's not scale, it's categorical. Now we have two options for categorical data, ordinal and nominal. SPSS gives you a little bit of help here, helping you remember which is which. Ordinal has groupings, but they have a step order to them because ordinal data is ordered. And nominal is just 3 bubbles, and there's no particular order because nominal data isn't ranked or ordered. Now gender, male, female, I can't rank males and females, so it's going to be nominal. Travel time. Now, as you can see from the data on the screen, travel time is just the travel time in minutes, how long it takes to commute. So there's no groupings. That means we can leave it as scale. All right, let's go to our data view and enter some data. We're going to have a look at the data on your screen. It's 0, 0, 0, 1, 0, 1. Now, if yours has zeros and ones, don't worry. It's just because my data file has the value labels icon pushed in or clicked. If I untick that, I can see my codes. Now, this is great because you can see on your data file whether you want to see value labels or numerical codes. Let's enter travel time. 35, 15. Okay, just before we close, I'm going to go back to variable view and make a few pointers. Really important, remember to put good value labels in. It's really important. So the label, the value label, this is what will appear on all of your output. If you take an extra 30 seconds to make a good label, then you don't have to relabel any of your output. Also, remember to be consistent in capitalization and punctuation, and please don't misspell anything that looks really bad on a graph. And the last thing is, for missing data, coding missing data is an option. It's not compulsory. But if you've got a huge data set or you've lots of missing values, it's probably a good idea so that you can keep track of your data. So if you do have a missing data code and you enter that into your data set, then you can define it here. So we've got gender and it has a missing value code of 999. So let's say, for example, this participant, participant 2, didn't specify their gender. I can then choose to code that as 999. And since I defined it in my variable view, SPSS will recognize that 999 to be missing. Okay, if you've got a questionnaire and you want to see more specific question types from a questionnaire, please have a look at those relevant videos. In this video, we're going to look at interpreting the percentages that we get from a cross-tabulation table. So let's go back to Analyze, Descriptive Statistics, and Crosstabs. Now I'm going to create the table that I did in the previous video for crosstabs, and I'm going to put gender as the row, and I'm going to put productivity as my column. I'm not going to choose any statistics, but I am going to go to the Cells tab because I want to show all 3 percentages, the row, the column, and the total. And we're going to look at how we interpret all 3 because we interpret them differently. Go ahead and click Continue, and we're not going to do any bar charts. Go ahead and click OK. Okay, so here's my crosstabs table. I have 3 percentages, a percentage within gender, which is my row percentage within productivity, which is my column percentage, and the percentage of total, which is my total percentage. Now, because I wanted you to be able to follow along with me a little bit better, I created a table earlier and I highlighted some of the cells so that you can tell what the totals are that we're using. So if I show you that one instead, okay, so here I've got my totals for my columns that are highlighted in green. I have my row totals for gender highlighted in yellow, and I have my overall sample total, which is highlighted in purple. So let's have a look at interpreting our percentages. Like I said, there's 3 of them, and we interpret all 3 differently. So I've written out 3 examples so that we can see the difference. So my percentage within gender, I'm going to look at males and average productivity, and I have 3 percentages. The first one should say 19.4%, so let's change that. Okay, so 19.4% of males have average productivity. So we get the 19.4% by taking 6 and dividing it by the male total, which is 31. So 19.4%. My second one here says 37.5%, which is here. 37.5% of participants with average productivity are male. Now this time I've taken the 6 and we divide it by the column total for average, which is 16. So 6 people out of the 16 who have average productivity are male. So we get 37.5%. Now my last percentage is with respect to my overall total. So this is my overall total number of participants, 69. So 6 participants out of 69 is 8.7%. And we interpret that as 8.7% of participants are male and have average productivity. So do you see the difference between the three? One of them is with respect to males, one of them is with respect to average productivity, and one of them is with respect to the overall total. It's really important that you get the interpretation of your percentages right and you use the one that you're intending to use. Okay, let's try one more and see if you can have a go at it. So we're going to use females and we're going to look at very good productivity. So I want you to pause and just have a go at interpreting all 3 of these percentages, and then we're going to interpret them together. Okay, have you had a go? Let's see if you got your interpretations correct. So we said female and very good, and we have 3 percentages. So the first one's with respect to gender, so 18.4% of females have very good productivity. The second is with respect to productivity, so we say 58.3% of participants with very good productivity are female. And the third one is with respect to the total. So 10.1% of participants are female and have very good productivity. In this video, I'm going to show you how to calculate a total score from 4 variables. Now you can do this for 2 or more variables. I have 4 satisfaction variables. All 4 are Likert scale questions from a questionnaire. And I'm going to tabulate a total score for each participant. So to do that, I'm going to compute a new variable, which is under the transform menu. I'm going to hit reset to get rid of what's there. I'm going to name my new variable, which is total score. Remember, no spaces or special characters. And I'm just simply going to add them together. So I'll click on the first variable and move it over, and then click the plus. The second variable, plus the third variable, plus the fourth variable. When you're done, go ahead and click OK. Go back to my data file, and I can see I have a new variable called total status. I'll go to the variable view, and I'm going to change the decimal places to 0, and then I'm going to go back. And just to show you that these are correct, let's have a look at our values. And if we add up the 4 satisfaction scores, it should be 11. So 5 and 3 is 8, plus 1 is 9, plus 2 is 11 for participant 1. So this is a total satisfaction score for each participant. In this video, I'll show you how to calculate a mean score as a variable. So say I have these 4 satisfaction scores. All 4 are Likert scale variables from a questionnaire, and I want to tabulate a variable which represents the mean score for each participant. So from the transform menu, I'm going to choose compute variable. I need to give my new variable a name. I'm going to call it mean satis. Remember, it can't have spaces or special characters. Now in this numeric expression box is where I'm going to tabulate my mean. There is a function in SPSS, and if you click on all, and then in the bottom there, find mean. If you hit M, it takes you straight down to all the M's. Once you find mean, you can either double click or you can use the arrow to move it up into the expression box. Now we're going to replace these question marks with the variables that we want to find the mean score for. So I'm going to use all 4 of these variables here. So I click on the first one, move it over. I'm going to highlight the next question mark, and I'm going to click on the second variable and move it over. Now I have more than two, so I'm going to separate them with a comma. So if I put a comma and then I click on the third variable, another comma, and then the fourth variable. And now I'm finished. I will find the mean of all four of these scores. So when you're done, go ahead and click OK. Go back to your data file, and you'll see I have a new variable called mean status. If I double click, I can go straight to the variable view. Make sure my level of measurement is correct. It is scale, which is right, and I'm going to give it a new label. I'm going to call it mean satisfaction score. The decimal places I'm going to leave as 2. If I go back to my data view, once again I can see that I have a new variable which represents the mean of all four satisfaction scores. I'm going to show you how to create dummy variables for a categorical variable. Now you'll need to do this if you want to use a nominal variable like I have here, ethnic group, in something like multiple regression. So I'm going to create a new variable for each one of my responses. And I have 5 possible responses. So if I double click on ethnic group, I can have a look at my variable view. If I go over to my value labels, I can see that I have 4 different ethnic groups listed: white, European, Asian, West Indian, African. I want to create a new variable for each one of these. So for example, if I create one for Asian, 1 means the participant's Asian, 0 means that they're not. The same thing for West Indian, African, and then for other. I'll go ahead and click OK and show you how to do this. If you go to transform, we're going to recode into different variables because I want to create new variables. I don't want to replace my existing data. I have some old data there, so I'm going to hit reset and find ethnic group, move it over to my variables box. I'm going to write the name of my variable, so I'm first going to create a dummy variable for white European. Click change. My variable name will appear in the output box. Click on old and new values. Now the old value for white European is 1. So if a participant is white European, the new value should also be 1. For all other ethnic groups, that would be all other values, I want to assign a value of 0, which means they're not that ethnic group. Go ahead and click continue and then OK. Go back to my data file. I can see a new variable called white European. I'm going to change the decimal places to 0. I'm going to change the level of measurement to nominal, and now I'm going to give it value labels. So if it takes a value of 1, that means the participant is white European. Make sure I click add. And if it has a value of 0, it means the participant is not white European. They are an other ethnic group. Click add. When you're done, go ahead and click OK. Now, if we have a look at the data view, I can see that for each participant, they're either white European or other, and my values are 1s and 0s. I'm going to repeat this process for one more ethnic group to show you how. We're going to do it for Asian. So if we go back to recode into different variables, make sure to click reset, move ethnic group over. The name of my variable is Asian. Click on change so that it shows in the box. Old and new values. My old value for Asian is 2. And the new value is going to be 1. That means if a participant is Asian, I want the value to be 1 for the new variable. All other values, I want them to be 0 because the participant is not Asian. Go ahead and click continue and then OK. If I go back to the variable, I can see I have a new variable called Asian, that's 0s and 1s. I need to give it value labels, so if I go to the variable view, I'm going to change decimals to 0. Again, I'm going to change my level of measure to nominal, and then I'm going to change my value labels. Now remember, the whole point of doing this was to create a dummy variable which is 0s and 1s. That's the definition of a dummy variable, which is why we are using 0s and 1s. So just like white European, I changed 1 to mean Asian and 0 to mean other. If I go back and have a look, I can see now that if a participant's white European, they should be other under Asian because they can't be both. Now you'd repeat this process for each possible ethnic group. So in this case, I would have 5 new variables, and they would all be zeros and ones. So 0 meaning no, and 1 meaning yes. I'm going to show you how to use the Recode into same variable option in SPSS. I will use the variable gender. Right now, female is coded as 1 and male is coded as 2, but I want to change that so that male is coded as 0 and female is still coded as 1. So from the transform menu, I'm going to recode into same variables, and this will replace the coding I have for gender. I'll move gender over to my variables box, and then I'll click on old and new values. Now my old value for male is 2, but my new value is 0, and I click add. My old value for female is 1, and I'm going to keep that same value, so I'll enter 1 under new value and click add. Once you're done, click continue and then click OK. The output box will always show first, so back to the variable view. I can see that the codes have been replaced for gender, so now there's zeros where there used to be male, but it does still say female. If I double click on my variable and go back to my value labels, I can change the coding for male. So instead of 2, 0 now represents male. I click change, and 1 is still female, so I click OK. And if I double click on the 3 and go back, I can see now that it says male and female. And if I click on my box up in the corner, I can see my numerical values are 0 and 1. If we had used the Recode into different variables option, a new variable for gender would have been created with a new coding of 0 and 1. But because we used Recode into same variable, the data I had under gender was replaced with my new code. So if you do not want to replace your existing data, then choose Recode into different variables. In this video, I want to show you how to recode a scale variable into an ordinal variable with categories. And the variable I'm going to show you with is age. And I'm going to use the Recode into different variable options under the transform menu. This will allow me to keep my original variable. And I will be creating a new variable. I'm going to move the variable age into my input variable box, and then I'm going to assign a name to my new variable, which is age groups. Remember, it can't have any spaces. And click change. This will move my variable name over into the box. Then click old and new values. And here we're going to specify the ranges for our groupings. So for the first one, I'm going to choose range lowest through, and I want to group for 25 and younger. So I'm going to enter 25. This is group 1, so under new value, I will enter 1 and then click add. For my next group, it's going to be 26 through 35, so I'm going to use this range option, and I'm going to enter 26 and then 35. Now this is group 2, and then click add. I'm going to continue this for the next 2 groups, so 36 to 45. This is group 3. And then 46 to 55. And that's group 4. Now for my last group, I want ages 56 and older, so I'm going to choose range, value through highest, and enter 56. This is group 5. And make sure to click add. I'm done now, so I can click on continue. And then I can also click OK. Your output window will be the first thing that shows, so I'm going to go back to my data file. And you can see my original variable is still there, so I'm going to scroll all the way to the right, and I can see my new variable called age groups with my categories 1 to 5. Now if I double click on the heading, I will be taken to the variable view and I can see my new variable there. I need to define it. I'm going to change my decimal places to 0, and I'm also going to give it a label. Next, I'm going to do value labels. So this is where I'm just going to put the groupings that I just created. So group 1 is under 25. Group 2 is 26 to 35. Group 3 is 36 to 45. Group 4 is 46 to 55. And the last group is 56 and older. Make sure to click Add after each one and click OK. So now I've done my value labels. The last thing I need to do is change my measure because it's no longer a scale variable, it's ordinal. And now that I've done that, I'm going to go look at my variable again in the data view. So if I double click on that 13, and you can see now that my value labels are showing because I have this box here checked. If I uncheck it, I can see my values. In this video, I'm going to show you how to reduce the number of groups of a categorical variable. So I'm going to change the variable satisfaction. It currently has 5 groups. It's a Likert scale from strongly disagree to strongly agree, and I'm going to change it to 3 groups. So if I go to the variable view, you can see my original coding from 1 to 5. I'm going to combine strongly disagree with disagree as a group. I'm going to leave undecided, and I'm going to combine agree and strongly agree. So the first 2 are going to make up group 1. Undecided will be a group on its own, and the last 2 will be the 3rd group. If I go to the transform menu, I'm going to choose recode into different variables because I want to create a new variable. I don't want to replace my existing data. I'll find satisfaction on the left, and I'm going to move it to the box on the right, and I'm going to give this variable a new name. Remember, you cannot use spaces or special characters. You can only use an underscore. Once I've entered the name, I'll hit change, and my new variable name will show in the box. Click on old and new values. My old value 1 for strongly disagree, that is going to stay as 1. So I'll enter 1 in old value, and I'm also going to enter 1 in new value. And then I'm going to click add. My second group 2 was disagree, and it's going to become group 1 as well because I'm going to combine it with strongly disagree, and click add. 3 is undecided, and undecided is going to be its group of its own. It's group 2, so my new value is a 2. And then agree was 4, and it's going to become group number 3. Likewise, group 5, which was strongly agree, is also going to become group 3. Make sure to click add each time. You can see my old values from 1 to 5, and now my new groupings are from 1 to 3. When you're done, click continue, and then click OK. Go back to your data file, and you'll see the new variable that you've created. I'm going to change the number of decimal places to 0, and I'm also going to give it a new label. I'm going to call it satisfaction with 3 groups. I'm also going to define value labels so I can see what 1, 2, and 3 represent. So 1 is disagree or strongly disagree. Because I've combined these 2 responses into 1, I'll click add, and my next group 2 is undecided. And my final group 3, I've combined agree with strongly agree. Make sure to click add each time. When you're finished, go ahead and click OK. And the last thing, we need to change the level of measurement, which is on the far right hand side. This is an ordinal variable. Now if we double click on the 13, which is next to our variable, it takes us back to our data view. we're just going to have a check and make sure that our data is correct. So I'm just going to click and drag my variable next to my satisfaction variable to compare. And I can see that the response agree is now agree or strongly agree. Disagree is with disagree or strongly agree. Undecided with undecided. So I can see that my data is in agreement with each other. And my new coding is from 1 to 3. You'll also notice there were zeros previously and now they're missing because I haven't coded my missing values yet. In this video, I'm going to show you how to reverse the coding of an ordinal variable. For this example, I'm going to reverse the coding for a variable called satisfaction, which is a Likert scale question from a questionnaire. Employees indicate their level of satisfaction with their position, and the values range between 1 and 5. Now if we double click on satisfaction, it could take us to the variable view, and if we click on our value labels, it will show that our current coding is 1 for strongly disagree, and all the way down to 5 equals strongly agree. And I want to change that so that 5 is strongly disagree, and then strongly agree is 1. So if we go to transform, and then we choose recode into different variables, because I want to create a new variable, I don't want to overwrite my existing data. Now I have something left over, so I'll hit reset, and then I will find my satisfaction variable in the left-hand side. And I'm going to move it over to my variables box, and then I need to give it a name. Remember, it can't have a space or a special character except for an underscore. And then I'll click change, and my variable name will appear in the box. Click on old and new values. Now my old value, 1, represents strongly disagree, and I'm going to change that to a 5. 2, for disagree, I want the new value to be 4. 3 is undecided, and it's going to stay unchanged, so I'm going to put 3 in my new value box. 4 for agree is going to become 2, and then 5 for strongly agree will become 1. And make sure to click add each time. Now you'll see my old coding from 1 to 5 is going to be changed to 5 to 1. Go ahead and click continue when you're done, and then click OK. Your output box will always show first. We'll go back to the data file, and we can see at the bottom of the variable view a new variable called satisfaction recode has been added. Change the decimal places to 0, and I'm going to go ahead and give it a new label. If I scroll over to the right, I'm going to change the measure to ordinal, and then I'm going to change my value labels and put in my new coding. So you remember I reversed my coding, so strongly agree was 1, but now it's 5. Make sure to click add, and then 4 is disagree. And 3 is undecided or neutral. 2 is agree. And 1 is strongly agree. Make sure to click add each time. Click OK, and then go back to the data view, and you can see I have my new variable on the very end. I'm going to move it over next to the other variable so I can compare the data. Now they should match. So if it was agree for the original variable, it should be agree for my new one. Same thing for disagree, disagree. I wrote neutral instead of undecided, but those should be the same. And if I look at my coding is different. It has been reversed. So 4s became 2s, 2 became 4, 3 stayed 3, 1 became 5, and 5s have become 1. You'll notice I have 2 missing values at the top. They were 0 in the original variable, but I have not coded my missing values yet. So they remain blank. I'm going to show you how to do an independent samples t-test. You do an independent t-test when you have one grouped variable, which is independent, and do you want to compare the mean score for a scale variable? I'm going to use total competency as my scale variable, and I want to compare the mean total competency between males and females. So I'm going to do a t-test. We can find the t-test under the Analyze menu and compare means, and it's the third option down, independent samples t-test. I'm going to find my scale variable, which is total competency, and move it to the test variable, and my grouping variable is gender. Now I have to define the groups, so click on Define Groups, and I have coded males and females as 0 and 1. So males are 0, females are 1. You need to use the codes you've used for your groups. Go ahead and click Continue. You also have the option of changing the confidence interval percentage, which is by default at 95%. I'm going to go ahead and leave it, so I'm going to click Continue and then click OK. Now I get two tables as my output. The first one is descriptive statistics and the second one has my t-test results. And we'll look at how to interpret these results in the next video. In this video, I'm going to show you how to create a scatter plot using two variables. I'm going to look at the relationship between age and an employee's total competency before starting their job to see if there's any relationship between the two. Now, total competency is my dependent variable because it depends upon the employee's age, so age is independent. We'll go to the chart builder under the graphs menu and I'll hit reset to clear my gallery. I'm going to choose the first scatter dot plot and drag it into my gallery. Now age is my independent variable, so it goes along the x-axis, and total competency is my dependent variable, so it goes on my y-axis. We're done, so let's click OK. Now I can see that there is a slight upward tending relationship, although there are a few outliers. So there might be a positive relationship between age and total competency, but I could do a correlation to find out if that's true. In this video, we're going to look at how to compute a Spearman row correlation coefficient. Now sometimes this is called Spearman's rank, or it's written as RS. Now the reason I'm going to use Spearman's row is because I want to correlate total competency of an employee before starting the job with their age group. And because age group is ordinal and categorical, I cannot use Pearson's R. So to do this, I'm going to go to Analyze and then Correlate, and I'm going to choose Bivariate because I have two variables. I'm going to reset this. I want to correlate total competency with age groups, so I'm going to move them over to my variables box. Now down here at the bottom I have some options to choose my correlation coefficient, and I don't want Pearson, I want to use Spearman. You also have test of significance, two-tailed or one-tailed. You should choose two-tailed if your alternate hypothesis is two-tailed, and by that it means you're stating there is a correlation, but you haven't said if it will be positive or negative. If, however, your alternate hypothesis says that there will be a positive relationship or correlation or a negative relationship or correlation, then you want to select one-tailed. I'm going to leave it as two-tailed for now. SPSS also asks if you want to flag significant correlations, and if you tick it, then SPSS will put one asterisk next to results that are significant at the 0.05 level, and it will put two asterisks if it's significant at the 0.01 level. So we can go ahead and click OK. And we can see our output here. Both of this box and this box are the same with here. This box and this box are the same. And that's perfectly normal for correlation output. And I'll explain what the figures mean in this output in the next video. In this video, I'm going to show you how to compute correlation coefficients using SPSS. I'm going to see if there's a relationship between total competency before employees start the job, and their age when they start the job. Now before I do this, I need to check that both these variables are approximately normally distributed. So I've created histograms. This is for total competency, and you can see it's roughly a bell-shaped curve. It's not perfect, but it would still be fair to use mean and standard deviation to sum up that distribution. And the same thing for age and years. It's not perfect, but it would be fair to use mean and standard deviation, so I'm going to consider it approximately normal. I also need to look for a linear relationship between competency and age, and I do that with a scatter plot. And you can see that the dots are tending upward in a straight line. There are a few outliers, but overall it's tending upwards. So I can go ahead and use Pearson's R, correlation coefficient. So from my data file, if I go to Analyze, Correlate, I'm going to choose Bivariate. I'm going to go ahead and hit Reset. And the two variables I want to correlate, I'm going to use a Pearson R correlation coefficient. And you can see there are two other correlation coefficients to choose from. I'm going to choose age and then total competency before they start the job. Now if these two variables had been not approximately normal or maybe not linear, then I would have used Spearman instead of Pearson. You can also indicate whether your test is two-tailed or one-tailed. If your hypothesis says that they'll be correlated but you're not sure if it's a negative or positive, then you want two-tailed. But if you're specifically saying that the relationship will be positive or it will be negative, then you want to choose one-tailed. You also have the option to flag significant correlations, so SPSS will put 1 asterisk next to results that are significant at 0.05 and 2 asterisks next to results significant at 0.01. Go ahead and click OK, and we can see here in our results that 2 of our results box are exactly the same, and that's completely normal. It shows the correlation coefficient of 0.228 and a significance of 0.060, and we're going to look at how to interpret this table in the next video. In this video, we're going to look at how to interpret the output of a Pearson correlation coefficient in SPSS. So what we've done is we've looked for a relationship between a person's age when they started their employment and their total competency score before they started their job. Now both of these are continuous scale variables, and we checked already that they were normally distributed and that they had a linear relationship, which is why we used Pearson's R correlation. So you can see across the diagonal that they're both 1, and that's because if we correlate a variable with itself, so age with age, it will be perfectly positively correlated. And if we correlate total competency with itself, it will be perfectly positively correlated. Now correlation coefficients are always between -1 and 1. And +1 means perfect positive, -1 means a perfect negative correlation. And that means they're exactly on a straight line. Now these correlation coefficients here are both the same because they're the same correlation. So this one is age with total competency, and this one is total competency with age. So it's actually showing the same thing. The first value is our actual correlation coefficient, and this tells us the strength of the linear relationship between our variables. And we can see here 0.228. If we were to look on a table, we would see that this is kind of a small, almost moderate strength, positive correlation because this value is positive. And the second thing I want to look at is my significance value, which is 0.060. Now I compare this to my level of significance. The level of significance I've chosen is 0.05. You may have chosen 0.01, so use the significance level that you're using for your test. And if this is greater than my level of significance, it means that my correlation isn't statistically significant. It means that it just occurred by chance. Because remember, we're using statistics because we have a sample, not a population. So what I'm saying is that in my sample, I observed a small positive correlation, but there's not enough evidence to say that this correlation exists in the population. If my significance value had been less than my level of significance, So this is my p-value. If it was less than 0.05, then I would have been able to say that there's enough evidence to suggest that the correlation we observed does exist in the population. But because this is greater than, we have to say that there's not enough evidence to show the correlation is significant. If you want to see me work through an example with a significant result, just have a look at the correlation interpretation for Spearman's row. In this video, we're going to look at interpreting the output in SPSS for a Spearman's row correlation coefficient. So this is my output table, and I've correlated the employee's total competency score before they start their job, and this is a continuous scale variable, with age groups. And because age groups is categorical, I have to use, well, it's categorical and it's ordinal, so I'm going to use Spearman's row. Now you can see here that this box on the lower left and this one on the upper right have the same information in them, and that's because they're the same correlation, they're just printed twice. So this one is for age groups with competency, and this is competency with age groups. So it's the same test, just showed twice. And we have ones across the diagonal because a variable correlated with itself will always be perfectly positively correlated. So remember, correlation coefficients range between -1 and +1. -1 means perfect negative correlation, and +1 means perfect positive correlation. So if we look here at our correlation coefficient, that's the first value here, it's 0.254. And if we look on a standard table to help us understand what that value means, we'll find that it's a small to moderate strength correlation. Now this value here, sig two-tailed, is our p-value, and this is going to help us know whether this correlation that we observed in our sample is actually statistically significant. So I'm going to compare that to my level of significance, which is my alpha, and my alpha is 0.05. Now because this value is smaller than my alpha value, I can conclude that I can accept my alternate hypothesis and say that the small to moderate positive correlation that I observed between employees' total competency and their age group is statistically significant. Now because mine is a two-tailed, my alternate hypothesis just said that there was a correlation. I didn't specify whether it would be positive or negative, which is why this is two-tailed. And the whole point of doing a statistical test for significance is because we have a sample and we're trying to determine if what we observed in our sample is true of the population. And that partly has to do with how the data was collected. So this test is assuming that the data was collected properly, it was a random sample, and it's representative of the population. And if that's true, then we can conclude there's enough evidence to suggest that a small to moderate positive correlation also exists in our population. Alright, in this video we're going to look at interpreting the output of an independent samples t-test. So if you remember from the previous video, we were comparing the mean total competency score of males and females, and this competency score was taken before starting their job. So we can see there was 31 males and 39 females in the sample. And the mean for males is slightly less than for females. Their standard deviations are about the same. This table down here is actually our t-test results. But before we know which line to read off of the t-test, because you see there's two lines here, there's this top one and there's the bottom one, we need to know whether or not we should assume that the variances are equal or not assume the variances are equal. And we do this with Levene's test for equality of variances here. We're given an F statistic and then we're given a significance value. And what this test is doing, the null hypothesis is that the variances of the two groups are approximately equal. That means that the distribution of competency scores for males is similar in shape to the distribution of competency scores for females. And the alternate hypothesis says that the two distributions are significantly different in shape. So we evaluate that using the significance value. And we do this the same that we would do all hypotheses tests. We're comparing it to our level of significance. Now I've set my level of significance to 0.05. You can choose 0.05 or 0.01 depending on what your significance level is. Now this value of 0.604 is much higher than 0.05, which means that I'm going to accept my null hypotheses and assume that the variances are approximately equal. Now that makes sense because if we look here at the standard deviation, which is just the square root of the variance, we can see that these two values are very, very similar. So it makes sense that we can assume equal variances. So now we know to read the first line of these results. We can see our t-statistic is minus 0.838, 68 degrees of freedom, and our significance value is 0.405. Now our significance value, we compare this again to our level of significance, which is 0.05. Now 0.405 is bigger than 0.05, so we are going to accept our null hypotheses, which says that the mean score between the groups is not significantly different. Now if we look over here, we are given a mean difference. Now this is obtained by taking the first mean, which is for the males, and subtracting the second mean, which is for the females. So if we have 40.94 minus 43.69, that gives us minus 2.757. Lastly, we're given a confidence interval. I've left mine at 95% because my level of significance is 0.05. And we're given a lower bound and an upper bound. Now this confidence interval is for the mean difference. So that means it's a confidence interval for this value here. So I can be 95% confident that the actual difference of the mean competency for males and females is between -9 and 3. That means that sometimes the men will have a smaller competency score than women, and then there's also a chance that the men could have a higher competency score, which is why we cannot say that there's a significant difference, because there's a chance it can go either way. In this video, I'm going to show you how to run a paired samples t-test. Now for a paired t-test, you need two repeated measures variables. I have total competency before an employee starts their job and total competency after 1 year on the job. So these two variables are my two repeated measures variables, and I'm going to see if there's a significant difference in the mean competency before and after. So if we go to Analyze, Compare Means, choose Paired Samples t-test. We're going to find our two variables in the list on the left. So the first one is total competency at T0, and then total competency at T2. And that comes as my first pair. I also have the option of changing the confidence interval percentage, which is by default at 95, but I'm going to leave it. Click OK. In the output, you'll see that there are 3 different tables. The first table is descriptive statistics showing the mean score for each variable, and the last one is the results for the t-test. And I'll show you how to interpret these in the next video. In this video, we're going to look at how to interpret the results of a paired samples t-test in SPSS. Now I have these 3 output tables, and I've done a paired samples t-test with 2 repeated measures variables. The first variable is total competency score of employees before they start their job, and then the same competency test 1 year after they've been on the job. And I want to see if the mean score of the 2 are significantly different. So I can see that the mean before they start their job is around 42, and that is less than their competency score on average after 1 year on the job. If I move down here to the third table, this is where the results of my t-test are. Under mean, there's a value of a minus 11.79. Now this is the mean difference between my 2 variables. So if I take 42.47 and I subtract 54.26, I'm going to get a value of minus 11. And SPSS always calculates the mean difference as the first mean minus the second mean. So it will always be that way. The standard deviation That's the standard deviation of my differences. That means that for each employee, we've calculated, or SPSS has calculated, a difference between their total competency before and total competency after. And then this is the standard deviation of all those differences. You don't have to worry too much about this value here. My t-statistic is the main thing I'm looking for, and it's quite large and negative. It's minus 26.062, which is a very small number. And that correlates to a very small significance value of 0.000. Now, we never say that this is 0 because it's not equal to 0. There's probably some digits there to the right that we just can't see. So what we usually say is that the significance value, or the p-value, which this is less than 0.001. And all that means is that it's very small and it's less than 0.001, but it's not equal to 0. So evaluating our t-test, we would reject the null hypotheses. The null hypothesis says that there's not a significant difference between the two mean scores, and we have found enough evidence to suggest that actually the difference between the two scores is statistically significant. And I know that because this value here is less than my significance, my level of significance, which is 0.05. Now your level of significance will be what you decide it to be. Usually it's 0.05 or 0.01. So you need to compare this to your level of significance. Now I've done a two-tailed test. So that means my alternate hypothesis was that there is a significant difference between the means. If you've done a one-tailed test, then generally you divide your two-tailed value by 2. Now because ours is so small, dividing by 2 isn't going to change anything. But if you have a larger significance value, sometimes dividing by 2 can make a difference. So if you have a one-tailed hypothesis that says a particular mean score will be significantly higher or significantly less than, then you have a one-tailed hypothesis and you would need to divide this value by 2. The last thing is the 95% confidence interval. You may or may not need this, but this is the confidence interval for the difference. So that means it's for this mean value here. And what it's saying is that we're 95% confident that the actual mean difference between total competency before and after 1 year on the job is between minus 12 and minus 10. And that means that we're very confident that the competency score before starting the job is always going to be less than the competency score after 1 year on the job. Okay, let's have a look at a chi-squared test when the assumptions have been violated. I'm going to do 2 examples. One is for a 2x2 table, and one is for a table that's bigger than 2x2. Now the advice I'm going to give in this video is from a couple of stats books. One is Andy Field's Discovering Statistics Using SPSS, his recommendation, and the other is one by Julie Poulant. Now, if your lecturer tells you something different, please do use their advice and what they want you to use, but this is just standard in most texts. Okay, let's look at our 2x2 example first. If we go to Analyze, Descriptives, and crosstabs, just as we did before, we're going to look at gender and smoking status. Under statistics, choose chi-squared, and the effect size, phi, will be the one we want to look at for a 2x2. Continue. Under cells, we want to tick expected because this is how we're going to check whether or not the assumptions have been violated. Click continue, and then click OK. Alright, in our output, here's our crosstabs table. Now the assumption for a 2x2 table, meaning 2 categories by 2 categories, is that all the expected counts are at least 10. Now you can see that 2 of them here, one is 7.8, one is 8.2, both less than 10, which means we violated that assumption. When that happens with a 2x2 table, we go down here and we can use Fisher's exact test. The likelihood ratio is also an option, but with just a 2x2 table, Fisher's exact test is common to use. I'm just going to use the two-sided figure here, and that's when your alternate hypothesis is two-tailed. In other words, you don't specify a direction of the difference. For example, you don't say there's more male smokers or more male non-smokers. You just say there is an association between gender and smoking status. Once you determine which significance value is best to use according to your alternate hypotheses, you want to compare it to your alpha just as usual. Now alpha, which is our level of significance, is typically 0.05. We can see that this is much bigger than 0.05, which means that a result is not significant, and we do accept the null hypothesis, also known as H0. Our null hypothesis in a chi-squared test is always there is not a significant difference, or not a significant association between the two variables. In other words, smoking status is completely independent of someone's gender. So that is the result that we would accept in this case because this is not significant. And when you get a non-significant result, you do not look down here at the effect size because it doesn't matter because the result is not significant. Now let's have a look at an example with a table bigger than 2 by 2. Here I have some insurance data, and the two variables we're going to use are the type of claim someone has filed and whether or not that claim turned out to be fraudulent. So let's conduct our chi-squared test as normal. Analyze descriptives, crosstabs, type of claim. Because this has more categories, I'm going to make it my row variable, and fraudulent is only 2. It's yes or no, so I'm going to make it my column, just so my table is easier to read. Statistics, chi-squared, and this time we're going to use Cramer's V. Continue. And in cells, I'm going to click expected, but it's not absolutely necessary this time. Click continue, and OK. Here's my crosstabs table. It's a bit bigger this time. It's bigger than a 2 by 2. And our assumption for a table bigger than 2 by 2 is that the expected count is not less than 5, or 20% of the cells have expected count greater than 5. So if we look down here at the bottom, it says 6 cells, or 60%, have expected count less than 5. This violates the assumption because 60% is much bigger than 20%. So I'll say it again, we want this value to be 20% or less, otherwise the assumption has been violated. If you need to rewind and listen to that again, go ahead. I know it's a lot to take in one go. When that's the case, we're going to read off the likelihood ratio. Here's my statistic, my degrees of freedom, and my significance value. Again, I'm going to compare it to my level of significance, 0.05. This is much bigger, which means I accept my null, and I conclude that there is no association between the type of claim and whether or not the claim is fraudulent. We're going to look at how to run a chi-squared test in SPSS and interpret the output. Now, I've got a database with some health statistics, and we're going to use gender and smoker or smoking status, so whether the person's a smoker or a non-smoker. Now, the reason I'm going to use these two is because we usually use a chi-squared test when we have two nominal variables. Now remember, nominal is data that has no meaningful rank or order. So smoker, non-smoker, male, female. They're definitely nominal variables. So let's go to Analyze, Descriptive Statistics, and Crosstabs. I'm going to reset. And I'm going to put in gender and smoker. It doesn't really matter which way around you do it. I've just chosen to put it this way. We're going to go to Cells, and I want to show you the expected count. I briefly mentioned this in the video on crosstabs. We're going to look at this in a bit more detail. I'm not going to use any percentages this time. And go ahead and click Continue. If we go to Statistics, we're going to tick the chi-squared option. Now, chi-squared is a test for independence, or you can think of it as a correlation coefficient, a test for an association. It just tells you if the association is significant, but doesn't tell you how strong it is. So we're going to use an effect size, either phi or Cramer's V, depending on the size of the table. So I'm going to go ahead and tick that box there. Go ahead and click Continue, and then click OK. Okay, let's look at our first table. This has our crosstabs, and we have our observed count, and we have our expected count. Now, the expected count is what we would expect to observe if there was no association. So, for example, if gender had no relationship with smoking status, so gender was independent from whether or not someone smoked, we would expect to observe around 39 males who are smokers and 47 or 48 males who are non-smokers. Similarly, we would expect to observe around 40 females who were smokers and around 49 females who were non-smokers. Now we can see our observed counts are different from these expected, and the chi-square test helps determine if those observed counts are different enough for the test to be significant or for the association to be significant. So let's look down here at our chi-squared test table. Now at the bottom, we need to read the first item, which tells us what percentage of the cells have expected count less than 5. This is important because it's an assumption of the chi-squared test. If this number here, this percentage, is greater than 20%, then this assumption has been violated and we need to take a different course of action. But for this example we're going to do now, this assumption has not been violated because 0 cells have an expected count less than 5. We can see the minimum is actually 39.05. In another example, I will show you what to do when that assumption is violated. Now, because this is okay, we're going to go up here and read the Pearson chi-squared value. It says 4.437. That's our chi-squared statistic. We have 1 degree of freedom, and this asymptotic significance is our p-value, or our significance value, and it's 0.035. Now most of the time you're going to be testing at the 5% level of significance. You might call that value alpha, and this value here, which is equivalent to 3.5%, is less than the alpha value. So that means our result would be statistically significant. And we would accept our alternate hypothesis, which says that there is a significant association between gender and smoking status. In other words, gender or smoking status is not independent from gender. It is dependent on gender. Okay, if we have a quick look down here at our phi and Kramer's V, because it's a 2x2 table, we're going to look at phi. If it was bigger, I would look at Kramer's V. And this is like an effect size or correlation coefficient. It tells us the size of the effect. So there's some standard tables to look at. I would recommend that you look at the one that your lecturer has given you or the textbook that you're using, because they do differ. In the book I use, which is The Survival Guide by Julie Pallant, 0.15 is approximately a small to moderate effect. So that means gender has a small to moderate effect on smoking status. And again, this is significant. In this video, we're going to look at how to use the Select Cases tool in SPSS so that we can select a specific range or cases of data to do our analysis on. So I'm going to do a couple of examples. The first one is just a simple one. I'm going to use gender, and I'm going to only select females to do my analysis. So I need to know what coding females are. If I take off my labels, I can see that I've labeled females with a 1. So if I want to select females, I need to use their code. If I go to data and select cases, I'm going to use a condition to satisfy in order to select my cases by. So I'm going to choose that option, click on if, and here I'm going to use gender to specify I want only females. So move over gender equals 1, because 1 is the coding for female. If I click continue and then OK, if I go back, I can see that all participants who are male have been slashed out. This means that any analysis I do from this point onward will exclude all male participants. So if I do a correlation or I get some descriptive statistics or make a chart or graph, it's only going to show data for female participants. Once you're done, make sure to go back and unselect those cases. Before we do that, I just want to show you at the end here, SPSS creates a filter variable, and it says selected or not selected. And you'll notice that these selected or not selected correspond to where the slashes are. So not selected gets a slash. These have been coded as 1s and 0s, and this is just for SPSS to know which data to use and which not to use. So do leave that variable in as long as you want to use the filter. If I want to take out the filter, I can just clear that, and then my selection disappears. I can also go back to data, select cases, and I can hit the reset button. Now what happens if I want to use a couple of groups from a data set. So I've got this rated skill here, and say I only want to look at fairly skilled or highly skilled. Let's have a look at our coding here for rated skill. If I go over to values, I can see it's unskilled, semi-skilled, fairly skilled, or highly skilled. And I just want to do some analysis on fairly skilled or highly skilled employees. So these are coded as 3 and 4. Go ahead and click OK. And I'm going to go back to select cases. And I'm going to do an if condition again. Click on if. This time, I'm going to use my rated skill of work. And if the rated skill is a 3, space, or space, if my rated skill is a 4, then I want to select those cases. It's really important that you have a space between on either side of the or otherwise it won't recognize it. If I go ahead and click continue, and then OK, go back to my data set, I can see now that all participants who are unskilled or semi-skilled have been slashed out. So if I do any analysis, it will not include these unskilled or semi-skilled workers. And again, I have a filter variable. Let's go ahead and clear that. Now the last example I want to do is, what if you want to specify an and condition? So for example, I want to look at females who are highly skilled. So that's an and, both female and highly skilled. Now, highly skilled is coded with a 4, and remember females are coded with a 1. So if I go back to data, select cases, if, I'm going to, actually let's hit cancel, let's reset this. If condition, gender equals 1, and make sure to put a space on either side, rated skill of work equals 4. Go ahead and click continue. Now one thing I didn't mention before is down here at the bottom you have a few options. You can choose to just filter out the unselected cases, which is what we've been doing. You can copy them to a new data set, or you can just delete the unselected cases. I wouldn't recommend the last option unless you've got backup copies of your data. This is actually useful if, say, you've got a huge data set with lots of people in it. But otherwise I would choose this one or the first option. Go ahead and click OK. Go back to our data set. Again, we can see there's a lot slashed out and only females who are highly skilled are left. Let's have a look at how we can edit our charts and graphs in SPSS. Now to access the chart editor, you either right click and choose Edit Content in separate window, or you can simply double click, which is what I'm going to do. So double click, and the chart editor has opened. You'll see in the background my chart is hashed out. That means I'm in chart editor mode, so in order to get back into my regular chart I need to make sure I close this when I'm finished. You also have a properties window. If you don't have one, or if you close it by accident, you can always open it again using this icon here. It says show properties window. Now the first thing I like to do is to resize my chart because this is too big to stick into a document, and when I shrink it down inside Microsoft Word it usually makes my font much too small. So I'm going to change it to 275. I'm always going to maintain the aspect ratio so that it looks correct. Okay, and now that my size is much better for putting into a document, I'm going to start editing parts of my chart. Now the first thing I want to do is I want to edit this label here because I think it's a bit long and clunky, and I just want it to say smoking status. Now in SPSS when you edit, you always want to single click. Single click your way through and you'll get what you want. If you try double clicking, you'll just end up frustrated. So I've single clicked, and now I want to go into the text and edit, so I single click again. So I'm going to highlight and put smoking status, which is much better. I can also come down here and I can single click my axes title, and I can single click again, and then I can edit if I want to. So maybe I don't want to have that in brackets. I can do the same thing for this title here. You'll notice that my graph doesn't have a title. I can put one on, and I can do that with this icon up here. So if I wanted to insert a title, and I could put status by gender, Okay, now let's look at how we can change these bars. Remember single click? So I'm going to single click, and when I do, I get a new properties window. I'm going to choose the fill and border tab. You'll notice that my fill is blocked out, so is my pattern, and that's because both of my bars are chosen, and they can't both be the same. So in order to unlock the fill, I need to just choose one category. I'm going to choose smoker, which is blue, so single click on smoker, and now my fill is unlocked. I'm going to go ahead and change this to orange. Click apply. You always have to click apply when you make a change. I'm going to single click on the green, and I'm going to change the pattern to a checker. Apply. You can also change the border if you wanted to. You can change the weight. So if I'm still on non-smoker, I could change the style of the border to say dashed. Okay, so now that I've changed the fill on the border, let's look at changing our axes labels. So if I single click on female, I can change the style. Now, I can also change the font type and my font size. The minimum size is the smallest font size. SPSS will make your font as you shrink your graph. So if I made my graph quite small, the minimum size would be 6. So I could increase that to 8, but first I have to increase my preferred size and then my minimum size. So SPSS will try to make your font a size 10, but if your chart gets too small, it will make it a size 8 because that's the minimum. Click apply. So it's going to increase it a bit. I can also change the scale on the left hand side. Now typically this scale doesn't need to be changed. It's fine as it is, but I can click on the scale tab and choose a minimum and maximum point, or if I want any margins, meaning some extra gaps at the bottom or at the top. Okay. In the chart editor, just have fun, play around, see what you can do. If you make a mistake, you can always use the undo option here and undo a disaster if one happens, because it happens sometimes. In the next video, I'm going to show you how to modify a scatterplot, because it's a different type of graph. This is our second example for editing a chart in the output file. This time we're going to look at a scatterplot. It's slightly different than a clustered bar chart, which we did before. Again, we're going to double click to get into our chart editor. And you know you're in the chart editor when you see the hashed out chart in the background. Again, first thing off, I'm going to change the size. Click apply. This way, when I put it into a document, it's resized and my font is the correct size as well. I can also change my legend titles. Remember, single click your way through charts. As I said in the last video, always single click, never double click. So if I want to edit what my legend title is, I single click, and then when I single click again, I can go in and edit it. So I'm just going to change this to say gender. So it's a bit shorter. Say I want to move my legend into my chart area. If I single click, I'm going to single click again, single click on the outside. There we go. That's what I want. So sometimes you have to single click around until you find what you want. I'm going to single click again on the outside. There we go. Now that I've got see, when I hover over the outside, I get this 4-way arrows here. That shows me that I can now move my legend. So you just need to single click around until you get this outside border. And then I'm going to move it in over here. So now it takes a little less space here on the outside. I also want to change my axes label. So again, single click. I'm going to change this to say age capitals, not lowercase. Now let's look at how we can format these bubbles. So I've done a grouped scatter plot, so I'm showing males and females separately for cholesterol level versus age. So say I want to make the shape different or the color a bit more pronounced so I can see the difference between males and females. I single click on any data point. This highlights all of them. Now say I want to change males, they're blue, so I need to single click on a blue dot. Now all the blue ones are highlighted, just males, and if I look over here at my properties window, I can now format just the males. I'm going to change my fill so it's a lighter shade of blue and click apply. I'm also going to change the design. So over here at the type, I'm going to choose a triangle and click apply. Okay, now they've gotten quite small, so let's change the size. I'm going to increase it to about 8. That's a little bit better. Okay, if I wanted to then format the dots for female, I would single click again, and then let's say I'll give that a fill. Okay, so now I've got females and males, and I've changed them slightly. Just as before, if you single click on the axes, you can change the minimum and preferred size for your font. Remember, the minimum size is the smallest the font will get as you shrink the size of your chart, and the preferred size is the size SPSS will try and make it until your chart gets too small and it has to move to the minimum size. And you can also change your font type. So I'm going to change it to Calibri and click Apply. Okay, you can also change the scales to the min-max points for both axes. Remember, just single click on the axes and then that will change. If your properties window gets closed, remember you can open it again using the properties icon up here at the top. Also, say you're doing a regression analysis, and this is a scatter plot for that regression, so maybe you're regressing males and females separately. You can actually add your fit lines. Now you can't see that very well. Let's see if I can try again. Up here at the top, you can add a fit line for the subgroups. So that means a fit line separately for males and females. You only do a fit line for subgroups if you're doing two separate regressions, one for male, one for female. If you're doing one regression model with gender as a variable, then you would just want one fit line for the total. And that gives me a fit line across there. Remember, don't just do a fit line just for the sake of doing one. Only do it if you're actually doing a regression and your data fit the assumption of a regression model. Have a go, play around with the chart editor. That's really the best way to figure out how to do things. And good luck. In the last example, we looked at selecting specific cases of data. This time we're going to look at taking a random sample. So say, for example, you have a huge database with thousands and thousands of cases or participants, and you just want to select a random sample of that database. You can do it using the Select Cases tool. So if you go back to Data, Select Cases, and instead of choosing the if condition like we did last time, we're going to choose either the first or the second. So random sample of cases. If I click on this and click sample, I can then choose if I want, say, 50% of all the cases. That would, so if I've got 70 in my data set now, it would randomly select 35 of them. Or I can specify exactly how many I want. So say, for example, I want to take exactly 50 from the first 70 cases. So I only have 70 in my data set. If you've got thousands and thousands, you may want to only select 100 from the first 1,000 or something to that effect. So you can choose how you randomly select your cases. I'm going to go back here and choose the approximately 50%. Click Continue. And then our output options, filter out unselected cases, or we could copy selected cases to a new data set or delete them. I said before, I don't like the delete option. I like to keep my original data set and either use filter out or copy. So say if I had a huge data set, I might want to copy them to a new data set. So I'm going to give it a name and call it random sample. And go ahead and click OK. Okay, so if we open up our new data set, I can see that it's called random sample. My data file is called untitled2, so I will need to name the file, but my data set has been named. And if I scroll down here, I've got 41 cases. And you might wonder, why do I have 41 when I asked for 50%? Well, it's approximately 50%, so it's around half of the data set. I should expect around 35. So in this case, it has selected 41, and I can see here by the ID column that it has taken a random sample from my original data set. If we go back to the original one, select cases again, this time I'm going to choose based on time or case range. So if you click on range, I can choose to select a range of cases. So say I want observations 10 through 20. Click continue, and this time I'm just going to filter out unselected cases. Click OK. And if we have a look, it's only cases 10 to 20 who have actually been selected. Now in this one, it's not really a random selection, but it is a different select case option. In In this video, we're going to look at how to use the split file tool in SPSS. Now, split file is different from select cases. Split file will split your data into different groups, and you can define those groups, and then it will analyze all the data in all the groups, whereas select cases is just selecting specific cases to analyze. So let's split our file by gender. And then we're going to create some descriptive statistics for males and females separately, just to give you an example. So if I go to Data and Split File, I have two options here. One is to compare groups, and one is to organize output by groups. Now this only affects the output of your analysis. If I choose Compare Groups, I'm going to get output for males and females in the same table. If I choose Organize Output by Groups, I will get a separate table for males and a separate table for females. So you can choose which you want. I'm going to choose Compare Groups so I get them in the same table. And gender is the variable by which I'm splitting my file. So I move it to my groups based on box. Make sure you leave Sort the File by Grouping Variables chosen, because it needs to be sorted, and then go ahead and click OK. If I go back to my data file, I can see that my file has been sorted by males and females. So all my males are first and all my females are second. Now if we go back to the output file, you'll see there's nothing here. There's just a log of what I did, but there's no output, and that's because I haven't done any analysis yet. In order to get output, I need to do something. So just to show you what the output's going to look like, let's go ahead and get some descriptive statistics for males and females. So Analyze, Descriptives. I'm going to use the frequencies options, just my preference. And let's look at gross annual income. Go to Statistics, and just going to choose a few, so mean, median, standard deviation, and range. You can choose any ones you want. Go ahead and click Continue. And I'm going to untick Display Frequency Tables because I don't want one. I just want my statistics, and click OK. Now you'll notice the output has come out in the same table, males on the top, females on the bottom, and I have my summary statistics here for each gender. If we go back up to Data and Split File, if I choose Organize Output by Groups, click OK, nothing's going to happen until I do an analysis, so let's go back and do what we did before. So Analyze Descriptives Frequencies, I'm going to leave Gross Annual Income there and go ahead and click OK. Now this time I get two separate tables. My first table is for male, here's my descriptives. My second table is for female, here is my descriptives. So for the split file, it just splits your file, like SPSS considers males and females to be two separate data files, but they're still in the same place. Now once you're done, remember to go back and unsplit your file. So I'm going to hit the reset button so it goes back to Analyze All Cases and click OK. Now my file is still remaining sorted. Now if you're quite particular about how your data set looks, you can go back and sort your file again by ID. So say you don't want to keep it this way. If we go to Data and Sort Cases, I'm going to choose to sort them by case number, which is my first one, and click OK. I'll go back to my data file. Now it's back to its original state and it's sorted by case number rather than by male and female. So that's how you use split file. In this video, I'm going to show you how to calculate a z-score for a variable using SPSS. The variable I'm going to use is total competency score for the employees, and this was taken at time 0, which is before they start their job. So if we go to Analyze, Descriptive Statistics, and then Descriptives, we want to find our competency score, which is the first one here on the list. Drag it to my variables box, and I want to tick Save Standardized Values as Variables. Standardized Values is just another name for a z-score. Go ahead and click OK. In the output, you're going to see a summary box of descriptive statistics for the variable with just the min, max, mean, and standard deviation. But we need to go to our data file to see the new variable. So I'm in the data view, and a new variable has been created, which is labeled with just a Z in front of the original variable name. So ZT0 total competency. And remember, the z-score is the number of standard deviations away from the mean. If we look here at our competency score, it's 27. And if we go back to our output, we can see the mean is 42. So the competency score of 27 is 1.13 standard deviations less than the mean. And that makes sense since our mean was higher than the competency score. Now, if you want to verify that this is the same output you would get if you calculated it on your own, you can use the data given in the output. However, don't use these rounded values. If you use the rounded values, you're going to get a slightly different answer. If you want to get a precise answer that is close to 5 or 6 decimal places to the one SPSS gives, you need to double click into this box and then double click on your data, and then you can see 6 decimal places of accuracy. So I'm just going to jot this mean value down, and then I'm going to go over here to standard deviation and also jot that down so that I can use it to compute my own z-score. If we go to transform and compute, I'm going to call this z-score STDEV. So I'm calculating a z-score using a standard deviation. Now remember, a z-score is always the value, which in this case would be competency, minus the mean, and we got the mean from our output, which was 42.471429, and we divide that by the standard deviation, which we copy down as well, which was 13.634697, and then go ahead and click OK. Go back to my data file. I've got my new variable here. I'm going to increase the decimal places to 5 so that I can compare it to my original one. And we can see it's really close. It's to 4 decimal places. If I wanted to get it more accurate, I'd probably need to calculate the mean and standard deviation to more than 6 decimal places to get a more precise answer, but it's pretty close. Okay, that's it.